stadium. It is for New Jersey Jets and Giants teams. It can sit about 80,000 people. In my experience, this is one of the fastest projects. It has 25,000 tons of steel. We won the project, and the minute we won the project, it has a very jumbo, large steel column sections. Because this is one stadium which had about, I would say about 18 to 19 meter column spacing throughout the stadium. It has a very high-end finishes and a pretty tall structure for a stadium. It's got 8 levels. So the columns were way above what the normal mill order sizes USA really fabricates rolls. So we have to go to Trade Arbor. That is the only steel rollers who build larger sections. So and they have very limited days. They roll only on certain days. So if you go on their website and you find out that you need to release the entire schedule in December, we won the job in November. The architect didn't even pick up the pencil to design the building. He just had some cartoon drawn. And basically we had to start, we had to order the steel. So I had a team of 15 engineers working. I remember it was before Christmas time, which for me is not a great holiday or not a big holiday, but all my other colleagues, they celebrate Christmas, and we had to sit for 2 months working till 4 o'clock in the morning every day, 8 o'clock in the morning, everybody's back, and we designed about 8,000 tons of steel in 2 weeks, talking to the architects without really getting drawings, making some good assumptions, and we placed an order. And if we had not placed that order, the next schedule would have been after 8 months. So the job would not have been built, or we would have to look for all the fabricated latex sections, and that would have taken a lot more time. So not only we were able to design, but 2 weeks putting the whole team together, we were able to order the steel. A lot of times people are a little bit negative about ordering the steel, that you cannot come back and change. But if you know what you're doing, if you're a good engineer, you can do it. Then of course there were changes, and of course we had to make some changes. But we were literally, if we thought the column was supposed to be here, we were able to use somewhere else. And maybe there was a little bit of wastage in the material, but we were able to save 8 months, which was far, far more important than losing 100 tons of steel. In USA, the stadium, especially the sports facility or any of these kind of venues, are very critical because they have their opening date is set in stone. Every delay in a day can cause huge penalties to the contractor. So this was a design-build project where the contractor was also on board, and that's why we were able to order the steel. So basically, the entire job was about 27,000 tons of steel. It was from the start of the design to the construction completion. It was 27 months from, like I say, schematic to topping out. Actually, it says topping out. That is right, but we started releasing some of the lower floors architecture. And basically, it was 3 to 6 months ahead of schedule. And when steel is ahead of schedule, there is a huge benefit because usually the steel and concrete is leading, because that's the first shell is the first thing we have to build. And that means if there are any other delays in any other trades, if steel is 6 months ahead, you are not breathing room to accommodate other changes, other delays. If steel gets delayed by 6 months, you know that all you are going to face is delays and delays and more delays. So these are just some of our 3D models. As Quantum Tomasetti, we do every project, whether it is a small stair opening we are working for a client in an existing building, or a large project like this. We do everything in 3D, and now we are going to build. And then after we started Meadowlands Stadium, we were contracted. Our scope was just to make the steel structure for the building. But then once they started realizing the bleachers, the precast, and they realized that there were so many mechanical utility pipes, steel connections and all that they felt that there would be a lot of clashes, and since precast is also made beforehand, they couldn't afford to have any clashes. So they kind of increased our scope, and they told us to add the precast bleachers also in our model, so they can really check everything, all of the trades also for clashes. And if you see, this job was only 60 tons of steel, but it was a very complex, very light, airy kind of structure, and we had to do big because otherwise we wouldn't have been able to design the connections. This is an airport hangar, so obviously it wasn't a very high, architecturally a very, critical project. But doing this kind of modeling beforehand really makes the job project complete faster, and it can really help a lot. These are just some expressions of modeling to drawings. Yankee Stadium. For this one, we were hired to design every single connection, which again helped the project to complete it on time. So besides designing the buildings, the other use steel has is even during construction. It really, like for a large venue, let's say if it is a concert hall, it's got an uninterrupted large roof, and obviously if the roof is built of steel, sometimes it's not possible to design, or even if you design, to fabricate and transport 100-meter long steel structure truss. So you have to design in piecemeal, because most of these places are in a busy city center, and roads are narrow, trucks are smaller, you still cannot transport whatever can fit in the truck, that's all you can fit in. So for something like that, sometimes you need to even have some kind of shoring or staging structure. So these kind of trusses, one end of the truss can sit on the staging truss, and then eventually the shoring or staging truss comes out. But so along with that, that's another powerful use of steel, because during construction, you can't make a big concrete pier or something to support these kind of trusses temporarily. But it's very easy to build something, scaffolding kind of truss quickly. You can assemble this, take it out, and even rebuild or reuse. So there is great advantage. Even in concrete foundations, sometimes you need to provide the slab before you can backfill the structure, because the wall is not stable on its own, and at that time, temporarily, for some reason, you cannot erect the slab. Then it's easy to provide shoring supports, and it's much easier to do this with steel. So basically, a structural engineer can integrate cutting-edge designs and construction deliverables. If we understand what the goals are, it is really very easy to do the extensive analysis, and then even review, understand how the construction will be done, and include that also incorporated in the design. So what we typically at Thornton Tomasetti, we have about a staff of 30 very sharp engineers who are very well versed with the software technology, and they are engineers also. And basically we call it our R&D group, and they are constantly trying to incorporate one software to other software, so we can save time and we can push our design limits, because otherwise if I had to sit and draw a very complicated curved structure, I'll be sitting and trying to draw on a board or trying to figure out the geometry from Excel spreadsheet. But the new trend is there isn't any time, so how we can incorporate all these so we can enhance our design and help the clients. So along with that, of course, with all these things, there are challenges we face. It's because we are in a transition phase. the fabricators, detailers, all the fabricators, details are not very well, they don't address these kind of deviations because they are just used to working certain way, and anytime there is a change, it takes time to translate. But still, if we get everyone on board beforehand, it really helps. And eventually, once there are positive results, now the clients come back to us and this is the only way they want us to proceed. More time? Do we still have time? Do I have more time? No. I have some other photos. Okay. This is something new we are developing, which we call it a parametric modeling. It's just something new we have been researching for the last 12 months, and we feel like this is where the industry is going to move from now onward. And I figure I'll just show you some interesting slide. I guess engineering and construction is a little bit boring, so I'll just use some sunflowers. The reason for this video is basically what we are trying to say is that the sunflowers, all these sunflowers, there is a driver for these sunflowers, and the driver is sun, because as the sun moves, the sunflowers also move along with the sun. So in the last decade, following the development of the aerospace, we all know that the aerospace industry is way ahead of the standard AEC industry, and they basically do the parametric modeling. But unlike them, we just use computer-aided drafting. But now what we are trying to do is adopt this parametric modeling into our design. And basically, the way the parametric modeling works is because there is a driver. If you define one object, if you connect all the variables to one object, then it really, as you change one object, all the variables will change. And this just allows the architects, the very high-end architects, because they just sit there and they come up with all these weird shapes, and every time, next day they change the shape, and before we understand the geometry of their first design, the design is changing. So what it does is, this is still BIM, but what we are trying to do is we are trying to use the BIM in the concept design. Until now we are using BIM in the CD phase, so we know that the model will be used by the steel contractors and detailers. But now what we are doing is we are trying to use BIM for the structural engineers, so we can adapt to the geometry of complex structures. And all it does is, rather than spending the time later, we are trying to spend that time before. I'll go really quick. So this is one of the tower we had done. This was, the architect just had a vision of using ribbons, and he didn't even know what was the final, design he was trying to use. And we tried to look at connect all the variables to one driver, one object. So every time we change one, all the other parameters will change accordingly, and you can see the final evolution of the design. Go faster because basically it is just a software we have written where it really helps them. This is in Basra. It's a 30,000 seat soccer stadium. And the architect, this is one of the leading sports architects in USA. And basically he wanted to have something like water. He sat down with us, and we are trying to develop what is something that he can vision, whatever he visions, we can build it. And from that model, what he had visioned, we tried to take that model, we put the entire geometry together where we can efficiently efficiently locate all the columns, along with that the building facade, the roof, because this is not one of the common kind of structures. So not only you need to make sure that you can understand the geometry right, but then you can analyze it right too. And then you don't have enough time. So the only way to do some of these things faster is if once you understand the basic concept, it can produce mass geometry, and we can incorporate it to SAP software where we can, as an engineer, we can analyze and then send it to the steel contractors where they can look into the fabrication. So these are just some of the images of some of these kind of complex structures happening nowadays. This one, as you can see, the facade was the biggest challenging. When the architect came up, there were like some 10 different variable of facade elements, and these things can get very expensive. This was in Basra, so it wasn't like it's sitting somewhere in UK or USA where the technology was way ahead. So we had to come and think of it, and I think a lot of the detailing was really done out of foundry. So what we were able to do is we were able to make all the parametric variables, and based on that we simplified the geometry, we reduced the number of variables, and we made out of 10, we can kind of